Purpose of this video is to continue talking about exponential functions, do a couple examples, and then do some word problems towards the end. I want to go back and look at a situation that we didn't really talk about, but we're going to do a problem with it right now. And that's when we had a situation like 1/2 to the x. Now we talked about when a was greater than 0, but we didn't look at the situation. Remember, a is always positive. We didn't look at this situation. Remember, a is not equal to 1. So let's investigate this situation. Let's see what happens and what the graph is going to look like. Okay? And actually, we should realize that 1/2 can be written as 2 to the negative 1. Okay? Remember, negative exponents just invert whatever we have. So if this is 2, 2 to the negative 1 is 1 over 2. Okay, so this is a property that we should know. Now, if I make use of that fact, I can rewrite my function as, instead of 1/2 here, I'm going to put 2 to the negative 1. And hopefully you guys remember the property with exponents, that if I have an exponent to an exponent, so if I had a to the x to the y, I just simply multiply. This is a to the xy. And so I have that situation here. I have an exponent to an exponent. And so I can just write that as 2 to the negative x. Well, wait a minute. I know what that looks like. Okay, I've done that in the last video. I've already looked at that, what that is equal to. And so basically 1/2 to the x is the same as 2 to the negative x. Okay, and I know what 2 to the negative x is. It looks like 2 to the x, except it's going to be reflected about the y-axis. Okay, and we know what 2 to the x looks like. So I get something like this. Okay, this is 2 to the negative x right here. And so if I'm in this situation, my domain and range are still the same. It's still infinity to negative infinity for domain, negative infinity to infinity for domain, 0 to infinity for range. But note that when we're in this situation, we are decreasing. Okay. Okay. So if I had 1/3 to the x, well, that's the same as 3 to the negative x. All right, and we know how to handle that negative exponent. All right, so the situation now between when a is between 0 and 1 is a situation that you guys should understand. Let's talk about this one-to-one property. Let's think about the graphs of the exponential function. They're either always increasing or always decreasing. All right, there was never a situation where we have relative maxes or mins when we just had a true exponential function. It passes the horizontal line test. Remember, the horizontal line test was telling me if the function was 1-to-1. And remember what 1-to-1 meant. 1-to-1 meant for each y, there is only one corresponding x in the domain. Okay, that's a quick summary right there. For each y value in the domain, there's only one corresponding x value in the domain. Okay? So for 1-to-1, we can use this 1-to-1 property for a is greater than 0 again, and a not equal to 1. If I have a to the x equals a to the y, that means that x is equal to y. And we're going to use that to solve some problems. Okay? So let's do that now. So if I have 2 to the x minus 3 is equal to 16, again, we have an equation here, we want to solve it. What I want to try to do is get the bases to be the same. And so I can rewrite 16 as 2 to the 4th. And so if I have 2 to the x minus 3 is equal to 2 to the 4th, that means that x minus 3 has to equal to 4, or x is going to be equal to 7. Okay? If I do this problem right here, 1/5 to the x plus 1 equals 125. Again, I want to get the same base here. I can rewrite 125 as 5 cubed. I can also redo this here as 1/5 to the negative third. Okay. Remember, if I want to get the same base as 1 over 5, I can simply say that 5 is equal to 1 over 5 to the negative 1. Okay, which is really saying 5 equals 1 to the negative 1 over 5 to the negative 1, which means I switch these, and this becomes 5 over 1, which is the same as 5. Then I just set the exponents equal to each other, and I get x is equal to -4. Okay? And basically, if I plug in -4 here, I'm going to get 1 over 5 to the -3rd power, which is equal to 1 to the -3rd, which is still 1, 5 to the -3rd, which is equal to 5 to the 3rd, over 1 to the 3rd, which is equal to 125. Okay? So that's how the negative exponent stuff. Don't get confused with negative exponents. All right? We talk about the natural exponential function. Natural base is the symbol e, which is 2.718. It's an irrational number. It continues forever. But this is going to be an important value. You're going to use this a lot in calculus. I want you to get very comfortable using the natural exponential function. Okay? We'll do a lot of practice with that and the natural logarithmic function, as you see. The graph, the shape of the graph is just like all the shapes that we saw before. Same properties, same domain, same range, always increasing. Just have a different base here. It's between 2 or 3. We're going to do a lot of applications with base E. You're going to use this a lot in calculus, so make sure that you really have a good understanding of it. Okay. Let's do a couple of applications. One is we talk about compound interest. And two different formulas that I want you guys to look at. We can have compound per year and a set number of times. And we have this with this equation here where A is the balance. P is the principal. That's your starting amount. How much did I start in my account? R is the annual interest rate, and that's in decimal form. So if I have R as my annual percentage rate, you know, R is equal to 6%. When I plug it in here, I want to put the 6% into decimal form. So here I would put in 0.06. Okay. N is the number of times I'm going to compound the interest, and T is the total number of times I'm looking at. Okay. So if I'm going to compound it yearly, N is going to be equal to 1. If I'm going to compound it monthly, N is going to be equal to 12. I'm going to compound it daily, I'm going to have N is equal to 365. Okay. For continuous compounding, same A, same P, mean the same thing, but now I'm going to have R times T, e to the RT, where again R is equal to the rate in decimal form. All right. Let's do an example using that. I have $5,000 to invest, and you have two options. You can either invest it at 5% compounded continuously, or invest it at 6% compounded monthly. Which investment will yield the most interest after 10 years? Well, let's look at each one individually. If I want to compound continuously, here is my equation. A is the amount, the initial investment P is 5,000, and R is equal to 0.05 here, and I want to know after 10 years. Okay, so here's my situation if I compound continuously. If I do that, after 10 years, I will have $8,243. Okay. Now what we want to do is compare that value if we compound monthly. Remember, we have a different rate this time. Our rate this time is going to be 6%. Our N here in monthly, N is going to equal 12. Okay, remember it's the number of times per year we're going to take the interest. So I got 0.06, I have 12, and then I have 12 times 10, okay? And if I do that, I have an interest rate of, I make $9,000, a little over $9,000, almost $9,100. Okay, so in this situation, compounding monthly was the way to go because of the higher interest rate. Okay? Let's do another example, which happens to be about radioactive decay. Let Q represent a mass of carbon-14. This is the half-life. Half-life means that after, if I start with, say, 100 grams of carbon-14, after 15 years, I'll only have 50 grams. I'll have half of what I started with. The quantity of carbon-14 present after T years is given by this equation. Okay, here's an exponential. I have a sort of a stretch here with that 10 in there. I determine the initial quantity. Well, the initial quantity is simply when T is equal to 0. So if I plug in T equals 0 here, remember anything to the 0th power is 1, so I start with 10 grams. So I'm starting with 10 grams here. And I want to know how much I have after 2,000 years. Again, so if I start with 10 grams, I plug in T is now equal to 2,000 into my equation, which tells me how much carbon-14 I'm going to have, and that's simply plugging it into the calculator. Make sure you guys know how to do this. When you do plug this into the calculator, make sure you put this term in parentheses. All right, so make sure you guys can stop and get that value. Okay, here's a graph of what that half-life equation was for carbon-14. All right, you can see that I'm gonna decrease, and as I go all the way, if I kept going to time, I'm gonna approach the horizontal asymptote, which is the x-axis. I want you to finish reading section 1. Again, look at some examples for me. Do some practice problems. These practice problems, couple word problems here at the end, using the one-to-one property to make sure you understand how to solve some pretty straightforward equations with exponentials. Again, if you have any questions, just email me. In this video, we looked at the one-to-one property. We looked at compound interest, and we looked at half-life, some more problems that involved exponentials. Okay, any questions, fellas, let me know, and have a nice day.